Jay, kick it off.
Hello,
Alright,
hello everyone. Hello.
Hi, everybody.
cool.
Hello.
Excited to get back into our contributor sync. It's been a while since we ran this. Daft has grown a lot. The architecture has grown a lot. There's been a lot of progress on the team. Very proud of where we are today. And yeah, just excited to get back in cadence, showing off what we've been building, a lot of the new model-based functionality, a lot of the new UDFs and architectural changes that enable us to get even better at the promise of multimodal data and AI over your data. So let's get started with maybe a high-level overview of what we've been cooking over the last, couple of months. So, high level, what we've been doing mostly really revolves around making running models on data very easy and performant. So some of the high level updates are number one, our new engine for distributed computing, Flotilla. It's now released. Hit the release notes. So 0.6.0, from 0.6 onwards, Flotilla is going to be the default runner when you run this in distributed mode. What that means is that you shouldn't have to flip any flags in order to use Flotilla. It's just plug and play, it will just work. And it now uses our local execution engine, which we previously codenamed Swordfish, in a distributed way. And again, you don't have to flip any flags for this to work. And later on in this chat, Colin's going to run us through a deep dive of how this Flotilla distributed engine kind of works under the hood, and also share some of the fresh off the press benchmark numbers for some of the multimodal workloads that we've been really optimizing, like audio transcription, video object detection, image classification, running models, document embedding, etc. So in line with that, we've also been working on a lot of model APIs and LLM operations. And so now if you go to the Daft documentation, you should start to see some of these new embed text, for example, is a new function that you can use. And embed text will just take a bunch of text and embed it and produce embeddings. We also have embed image. Very similar, you pass in an image column. And so, now you can go URLs into data, binary, into images, into embeddings, all within almost like 4 lines of code. And we just kind of make that work. What's really cool is that we also made the system very pluggable. And we introduced a new idea, a concept of a provider. Um, Providers can provide functionality such as embed image, embed text, and allow us to plug and play different providers such as OpenAI, also common Python libraries like sentence transformers, in order to run a lot of these operations. And there's going to be a very rich ecosystem that we continue to invest in and to make running models on your data really fast, efficient, and easy to get started with, and eventually, no pun intended, run on the eventual platform as well. Um, Cool. Along with that, we're improving UDFs quite a bit. We have Kevin on the call with us who can maybe run us through some of the thoughts here. But like I guess high level, we are introducing a new daft func, which allows us to write very simple scalar UDFs. We're introducing also functionality over these UDFs to do generators and also async functionality, which is centered around the new daft func syntax. But I'll let Kevin maybe take it over for a little bit here and run us through some of the work that's been going on.
Yeah, sure. So the stuff that Jay talked about in Daft Funk, the new like row-wise UDF that we have, along with the generator and async UDFs are all out there already. So um, you're welcome to play with it with our latest version of Daft. What we want to do going forward as well is to one improve the performance of this, especially for many of the use cases that we're seeing people use row-wise UDFs for, as well as improve the like usability of a lot of different things, such as like returning like complex data types, such as like nested, like NumPy arrays or pill images, as well as being able to do things like run a model in a UDF and specify the things that you want so that it is performant. So one thing that in particular that we're focusing on is like performance for a UDF call, which may take like a pretty long time, right? So something like if you're doing document processing or if you're doing model inference, each individual UDF call will take anywhere between like seconds to even minutes long. And so for that right now, the sort of like batch paradigm that Daft and many other like engines work with, don't exactly fit that need. And so we're trying to figure out how to improve our UDF performance for that kind of thing as well. So you'll be seeing a lot of new things coming up in the next week or two for this.
Yeah, super exciting. And I think instead of having one big monolithic UDF, now we have simple UDFs to do simple functionality. So if you're just doing things on a row level, just writing some Python code per row, the simple scalar UDF is your friend. If you're trying to, yield multiple items, like kind of like exploding an item, the generator UDF is your friend. If you're trying to do like calls out to the network, right? Maybe OpenAI or some other endpoint, then this async UDF is your friend. You don't really have to think that hard around like using async IO, just kind of mark everything as async like that, return await. Um, and yeah, lastly, if you're trying to do batch stuff, we also still have this batch kind of fallback for you to run this stuff. So that's it for UDFs. More to come. Hopefully, I'm hoping for the next contributor sync for us to focus on UDFs. That's going to be a big part of the next contributor sync and all the improvements that will come along there. Um, we have also been working really hard on Turbopuffer integrations, and so this is a example of how you can generate text embeddings and directly ship this into a vector database such as Turbopuffer. We've been working pretty closely with the team there to make this happen. And a full-on example of how to do this, along with like just maximum GPU utilization while you're doing this, right? And so here's the code examples for it. I have Desmond on the call as well, who maybe you want to run us through quickly, 1 or 2 minutes, Desmond, what the work here was?
Yeah, I mean, we have a couple of examples here. This one specifically is on embedding text documents. So if you have a bunch of text, you can split it. Usually people either split it into semantic chunks or like sentences. And then eventually you want to apply an embedding model on this. Here we use Quinn3, but a lot of other customers or users, they tend to use OpenAI or Gemini to do these embeddings. And then afterwards, you can directly use our new method on data frames called write Turbopuffer. Just provide a namespace, region. You do need a Turbopuffer API key, but if you do this, we do the distributed writes for you automatically. It works great. Give it a shot.
Yeah, super cool. So again, run models on data. Embedding models are also models, and we're gonna be doing a much better job at getting all this data through at a high throughput into your destination, which is usually for embedding something like a vector database or like Postgres, right, with PG Vector. Um, Next up, we have a new into batches DataFrame API. I'm really excited about this. It really reduces all the headache that people often have to work with for partitions. What this lets you do is it defines kind of the granularity of how Daft emits batches of data from the engine into the next step, right? And so I'm not sure if you have an example on this PR, but the way that you would use this is you would just insert this as part of the data frame call. Let's see. Yeah, I don't think there's an example on this PR, but we should make an example for this and we'll put it on the documentation. But the way that you would use this is you would kind of say, hey, I have a step that maybe by default you would think emits like a couple of thousand rows, and you want it to emit much smaller rows, like 32 rows at a time, because you know that it's going to be large. And you can kind of just insert that as part of the data frame and then have it emit much smaller batches at a time. This will reduce memory pressure downstream at the cost of a little bit higher overhead in your kind of overall pipeline. But if you want more granular control around memory in your pipeline, this is what you would use into batches. Check it out. Next, we have simple data sync into Clickhouse. Clickhouse is one of my favorite databases. Sorry, all other databases, but Clickhouse is amazing. And yeah, we have a community contribution into Daft, adding a data sync into so that Daft can now write into Clickhouse. I'm particularly excited about this because Clickhouse is pretty good with things like JSON and strings. And so you can imagine use cases such as, say captioning images or summarizing text and then just dumping it all in the Clickhouse so that you can kind of do your downstream real-time, time series analyses, which is what Clickhouse really excels at. Cool. And then now we have a bunch of work also happening now with some of our partners. on writing out Lance integrations. So Lance is another vector database, and our partners are pretty interested in building out much higher Lance support. Wondering here, Kevin, do you have any more context on the roadmap that you might want to share?
Um, I don't have too much stuff. We do have this is like very like community driven, I would say, from our uh, friends at ByteDance who are very interested in getting our integrations with Lance. So some of the things that they've been doing are on the like optimization side, things like improving our count star performance with Lance, adding things like our what was it? Um, several like push downs and other optimizations that allow people to work with like Lance tables, especially like sort of like Lance blob data and like larger data that's non-tabular within Lance and execute it very efficiently within Daft as well. Yeah.
Cool. Yeah, so keep your eye on this. I think there's quite a bit of movement. And yeah, excited to support more of these exotic multimodal data sources. Um, and lastly, very exciting, we have a new file type. Files are coming. I think what we realized as we started implementing things like, images, and now we're looking at a new video type as well, is that at the end of the day, this feels as if Daft just needs to be get really just needs to get really, really good at files, right? Like files represented by URLs, files that are lazily loaded, and files that can actually just be handed off into Python so that Python code can run over it and you can use any kind of library that's used to working with the Python file interface. So what that looks like is that now we have a daft.File type. We have kind of an initial MVP with local files and memory support. We also do support now S3, HTTP, and also this buffered reading. What that looks like in practice is here's some usage with the scalar UDFs that we talked about from before. If you are just reading from a single file and returning bytes, that's as simple as, define a UDF, you have a file input, and bytes output, and you just call it as if it was a normal Python file. .read is a kind of the interface to read data from the file. What's cool about this is that, if you wanted to, you could actually, use any other Python library that works on Python files inside of your UDFs now, and it just kind of works out of the box, right? So if you wanted to do any video processing with a Python video library, or you wanted to do some audio processing, that's all possible now because Daft is able to kind of just represent its data as this lazily loaded file that it provides to your library to do all this I/O at runtime. So we're super excited about this. I think that this kind of represents the future of how Daft will work with just a bucket full of files and objects, and that will enable us to support much more complicated data types that it's not possible for us to support all the possible encodings and file types in the world, but by returning this very flexible file object, we're able to do it. So here are some more upcoming pieces of functionality. We're going to be adding the ability to configure how chunky to read these files in with a kind of little Daft context. We're also adding temp file integration so that you can kind of like write the thing to a temporary file and use it from, within things like ffmpeg. So you can literally just run ffmpeg from within your UDS and it should just work. We're also going to be allowing you to write to files and produce a new file type, but actually backed by something like S3, which will be really cool. And you can kind of have your files flow through your pipeline, but actually have Daft do all the I/O with a remote file system, such as S3. And then lastly, yeah, integrating files a lot more closely with Daft itself. So a new table function such as daft.FromFiles to give you a single column of the file data type, which will replace kind of what we have today, which is from glob paths that gives you just URLs, right? Which really aren't as usable as these file types. Yeah, so a lot more to come on this end. We will be building a lot more material and a lot more testing, and also just making sure that this stuff is stable in a distributed setting in the next couple of months, but hoping to give folks much deeper dive the next time we run this session. Cool. So with that, we'd love to turn it across to Colin to do maybe a deeper dive into Flotilla, the distributed engine, which we are super excited to release in this 0.6 version. I think that Flotilla represents the culmination of, I think, more than a year's work at this point of designing the new streaming execution engine within Daft to run on your laptop, but then Flotilla now runs it on a cluster, which gives you really good memory stability, the ability to run models, the ability to work with multimodal data, all, kind of very seamlessly from your laptop to a cluster. And so, yeah, I'll turn it across to you, Colin, to drive this part of it.
Yeah, so cool. Let me share my screen. Cool. Let's see. Okay. Here, all right, we have images. All right, what do we want to do with these images? We want to run inference on these images. We want to classify them, and then we want to save them somewhere with all each image and a label of what they are. If you're a company that's processing large amounts of images daily from your users and you want to know what kind of category these images are, this is kind of a pipeline that might be very suited for you. And so let me just run this script real quick first, let it run, and then I'm going to explain exactly what's going to happen. Right. All right. So in Daft, right? Daft is a different library. We can read Parquet files, and then we can let's see what those Parquet files look like. So right here, you can see that we have a lot of image URLs. And in Daft, you can also see, okay, let's see how many images do I have today. I have roughly 800,000 images that I want to run classification over. Let's see some samples of these images. We can go over here. Bam. All right. Looks like we got some chickens. Very nice. Some other birds and birds over here like this. Let's see what, the labels of these images actually are. So we'll run a sample, just a .show, and then let's see. Cool. Looks like we got hens, house finches, water ouzel, and a great gray owl. Not sure what these are, but cool. We managed to do image classification on my local laptop. But the thing is, like, remember, we had 800,000 images here. So how are we actually going to run this efficiently, right? And the nice thing about Daft is that we can run distributed as well. We can run this this image classification pipeline on a array cluster. In this case, the script I ran over here, the one I ran in my terminal is running this script where the only thing we need to do is call set run array, and it's going to allow Daft to run distributed, right? This is what Flotilla is all about. We're trying to make it easy for you to run the same query that you run locally on a distributed cluster. And so let's actually take a look at the array dashboard. Let's see what's going on. If you see the query is running, it's around 2 minutes now. Let's look at the cluster. And you can see we get pretty good CPU utilization, memory utilization, and GPU utilization, right? We also get really good I/O throughput. All the URLs are getting downloaded as we are able to run inference, as we are able to run pre-processing, right? So what's actually going on here? Let's look at the jobs. You can see that when Daft runs something distributed on Flotilla now, we're going to spin up what we call swordfish actors. And these are basically workers on each node that are running the local swordfish engine on that node. And each of them receive a task, and they will run that task as if it's running just on a single machine. And in this case, it's a chain of tasks containing the scan of the Parquet file, the URL download, the inference for getting the label, and then writing all the results down to Parquet. It is pretty much the same thing that like we're doing here, except each kind of worker is going to take in like a partition of data or like a different file for it to read. As you can see, we managed to get this done in 3 minutes, sorry. And these are the file paths of the results that we were able to produce. And yay, Flotilla was able to classify almost 800,000 images in roughly in 3 minutes. And let's actually see what happens if we don't use Flotilla, right? Let's see what happens if we use our old array runner and why we were so compelled to use to build a new engine, right? So we can do this by setting the legacy array runner to true. And then let's just run it. All right. As you can see, there's one task. There's only one task here compared to the 8 that we saw just now. All right, let's look at the cluster. And we can see like this node here, this one is kind of the only one doing a lot of work. And like the rest of them aren't really doing anything. Right. And the reason for this is basically our old array runner, the previous one, was highly catered towards tabular workloads, analytical workloads, where each row is extremely small. So the old array runner was able to basically merge like partitions and tasks into a single like task because it thought that each row is going to be very small. The input data, as we had here, um, it's just metadata. It's just file paths. It didn't actually contain the images. So the old array runner thought, all right, let me just merge all of them together, and we'll just run one task. As you can see, things are probably gonna get out of hand pretty soon. And this is gonna start exploding into memory, and it's gonna eventually run out of memory. So what can we do then in this case with the old array runner? We can do something called a repartition. And let me show you what that looks like. And typically the guideline is that what we said was, hey, let's repartition into 2 times the number of CPUs. So I'm going to do 128 here.
Oh, I think you might need to do df repartition, Colin.
Oh, yeah. It's a good call. Thank you. Right. So now this should be okay, right? We're going to just split our inputs across 128 different tasks. We're going to get good utilization now. It's not just going to go onto one node. And then we're going to actually, make some progress with the old array runner. So let's take a look. Okay. We get good CPU utilization. Memory is going up. We are receiving a lot of data. Not much GPU. Oops, not much GPU yet. Okay, cool. Memory's still going up. Ooh, memory really went up. What is going on? What is going on, old array runner? Come on, you're supposed to be good at this. And no, sadly, the old array runner was definitely not good at these kinds of multimodal work. Look, it's just running out of memory. All the tasks are pretty much dying. And so we built a new array runner. We built Flotilla just to solve this exact problem. And because we're using our Swordfish engine instead of just simple array tasks, now we get this streaming kind of execution on each node, and we're able to reduce peak memory usage. We're going to get good I/O CPU utilization all throughout the entire pipeline. And if you are curious as to exactly how this works, if you go to our discussions page, if you go to the roadmap, here we have a design doc on Flotilla to explain exactly how it works, the background, why did we build this, the problems that we had with the old array runner, and the goals of Flotilla, some existing work, i.e. Swordfish, our streaming execution engine, so on and so forth, and some design docs on how Flotilla works as a whole. But yeah, Flotilla is now released in 0.6. Feel free to try it out. Feel free to use it on your multimodal workloads and let us know how it goes.
Cool. Thanks for the walkthrough, Colin. And I think we're doing a blog post soon, so keep your eyes peeled for more details about Flotilla. And we're going to be just churning out a lot more benchmarks, tutorials, just making sure that everyone has access to this really cool piece of technology that we've been developing for the last few months. I think that's it for us today. Let's turn it over to Chan Chan to wrap it up for us.
I did forget to mention the benchmarks. So
Yes, let's
I,
dive into
I
that.
showed I showed Flotilla versus the old array runner, but we actually did a lot of benchmarks on Flotilla versus a couple other engines that people would typically use for this, particularly Ray Data and Spark. And so we benchmarked Flotilla on 4 different kinds of multimodal workloads against Ray Data and Spark. these 4 workloads being audio transcription, document embedding, image classification, the one that I just showed you just now, and video object detection. Each one uses some kind of model. It runs some kind of model over your data. It uses GPUs and it writes these classified labels, embeddings to Parquet. And yeah, as you can see, we really put a lot of effort into Flotilla, and we really wanted to make it really, really good and better than the traditional engines that you would typically have been using for these kinds of multimodal workloads.
Super cool. Maybe run us through some of the numbers below in the table.
Yeah, so on all of these, it's I think we did pretty well. We're roughly at least 2x better than Ray Data, at least 4x better than EMR Spark on some of these workloads. And what's like really interesting is that this is a log scale graph, right? And in particular on the video detection one, you can see that Spark took 216 seconds, whereas we took 11 seconds. And the whole reason is like Spark doesn't understand that like each row is a massive video, right? It has no idea. So you need to do a lot of manual tuning, like repartitioning, telling it to just run one thing at a time, checkpointing, all these kind of things just to make it not Otherwise, it's gonna think that like, okay, I'm just gonna make batches of like 100,000 rows because it's tabular analytics, and that's just not possible with Spark. But with DAF, we're able to we understand that you're running these large multimodal workloads. We're going to batch size accordingly. We're going to pipeline IO, compute, and GPU, and we're going to get good utilization. We're going to save you money, and yeah.
Awesome. Yeah, thanks for the run through. I'm glad we didn't forget to run through the benchmarks today. Over to you, Chan Chan.
Cool. I think that wraps up our contributor sync for today. We'll be doing this every month again on the last Thursday of every month. So if anybody has like topics that they want to hear about next time, I've attached the agenda document on the calendar invite. So feel free to comment anything that you would like us to see next time. And I guess we're looking forward to Kevin and UDF deep dive next month. Cool. Okay, I think that's all for today. Thank you, everybody. Bye.